Just let me put this on. Okay. Yeah, hello. So yeah, I'm Bruno. I'm going to be talking about some realizability stuff that I've been looking at with my supervisor, Vincent. I presume this is perfect. Yeah. So this is all, first of all, this is all very quite work in progress. So I don't know, bear with me. But so what was my motivation? Basically, so got interested in choice sequences. That this was originally through the Brouwer, and I think, yeah, the idea is that they are these infinite sequences that whose values are being generated like in a sort of possibly non-deterministic way. But like at any point in time, we only have access to a finite number of the entries on the sequence. Like, so I think for Brouwer, like Brouwer was thinking of a mathematician like generating the sequence as they like work through the mathematical proof. And so like that's why there's only ever a finite number of values, for example, available. They're anti-classical. That's kind of why I find them interesting. But like Brouwer used them for an account of analysis, like real analysis, which is typically quite difficult to do constructively. Why? So me, my supervisor, and some other people, like we were looking at them. For example, they're helpful for sort of, yeah, giving you results like, oh, this version of Markov's principle is like, consistent, or like, yeah, it's consistent or not, and so on. And so like we had these different versions of Markov's principle, and we were trying to show that they weren't all equivalent, for example. But so that's where we sort of started. And then we were doing this by mixing in some form of realizability, but in a more like computational type theory sense of realizability. And so then we were interested in seeing if we could fit it into a categorical setting. So just to talk a bit more about choice sequences, normally, like to have if you want claim that you have like choice sequences, I guess these are like some sort of axioms that you would expect to find. First of all, so like we have this density axiom. This just says that there's like, for whatever like finite list you want, you're going to be able to find a choice sequence that will like whose values will be generated at the start according to that list, and then eventually they'll be freely generated. So that's quite important. That's very important in to talk about the analysis, because it's kind of what makes the Brouwer's reals uncountable, I think. Is it, or like complete? Yeah. But then decidability of equality. So like, yeah, equality of choice sequences specifically is decidable. So I mean, I guess I forgot to mention. So I have a type of choice sequences, or like we want to have a type of choice sequences, and these will give you functions from that to that. So these are obviously like equality here is not decidable, but like for choice sequences themselves, it should be. And then this axiom of open data is a kind of so this is like a continuity property, which says that if you have a predicate on choice sequences that holds for a specific choice sequence, then it can only examine a finite number of entries on the choice sequence. So if other choice sequences agree on the first n entries, then sigma will also hold. So those are the sort of axioms we expect. So like, it's kind of choice sequences are sort of computational, especially with this like open data thing. But so yeah, not really. I don't remember. To be honest, yeah, I've kind of forgotten where this crops up usually. I will find out and get back to you in person. Yeah, no, so sorry, no, not from Brouwer. Good point. Yeah, but so for talking about choice sequences, I think this is like a fairly well-established thing. Like sheaves are are fairly, or categories of sheaves are a natural setting for talking about choice sequences. Because if you're talking about choice sequences in a first order setting or whatever, you're gonna give semantics through uh, oh, yeah, crypty and bet style semantics. But then when you want to go higher order, like that's going to naturally lead you to pre-sheaves and sheaves. So we're going to be looking at our base category is this rooted tree of worlds. So it's seen as a post set. And on the topic of the bets semantics, right, we're going to have this for each world, so if you give me a world and an upwards closed subset of worlds, I'm going to say that that covers W if all paths which start at W will eventually reach U. So this is what's going to give you your notion of like Grothendieck topology for the sheaves, at least that I'm interested in. Yeah, so once we have that, then what I sort of want to, at least like the main intuition I think I want people to take away for the relation between choice sequences and sheaves is that like if you start with the pure natural numbers in pre-sheaves, which is like the constant pre-sheaf of natural numbers, then if I have a natural number at this world, it's like going to immediately have a value 3, and then that, regardless of how I move through this post set, like that value is going to be fixed. Once I take the sheafification of the natural numbers, so I have, I'm taking, I think it's A for like the associated sheaf. It's terrible. I need a new, anyways. Now the elements of the sheafification are going to be, so an element at world W doesn't necessarily have a value yet. What I know is that there exists a cover of W where we will always have a value, but then we're allowed to change values in some, well, sort of. So like, once I get a value, then like in all future extensions, I'm fixed in what that value must be. So like I'll have 3 going like, in all of those futures. But then, for example, I can have 4s in this sort of different path. And through here, I could eventually be 6. And like the sheafification of natural numbers allows you to have stuff like this, which is so I guess what I'm arguing is this is a sort of the similar non-determinism to what you need for choice sequences. Slight issue, like, the previous, like these axioms are now not going to be, these don't hold for like what I'm proposing as like the space of choice sequences, which is like functions from pure nats into this sheafified nats. Which is where like realizability comes in, because then we'll try to put some sort of computation to back sheaves, and like then the stuff that we'll have realizers will actually be behaving like a choice sequence. So like there's a sort of first attempt. This was my first attempt at formalizing this in a tripos over pre-sheaves, which was like, we're going to start with a PCA that has an application that's indexed by worlds and like, yes. No, so I mean, yeah, but I mean more that because I want decidability of equality for like the space of choice sequences, not for the sheafified natural numbers. Yeah, or yeah, exactly. So yeah, this was the sort of first attempt. And I think this is like the main idea is that like our PCA is going to be indexed by worlds, like, or the application is indexed by worlds, and you need some like monotonicity requirements on that. And then your realizability predicates are like natural, or given a pre-sheaf will be natural transformations from X to, and this is the power set of just like I forgot. Well, these are the sort of box stable propositions. So yeah. Oh, spoilers. Uh, but the point is, so we're gonna have a code A, and that's if that's in phi at W of X, that means that A is evidence that phi or that X satisfies the property phi at world W. And then when we want to order these predicates, we're gonna say that, so normally we want to say there exists a uniform way of sending realizers of phi to psi. And so, but now we have to care about worlds as well. So we're saying there exists a code that works for, so I think sorry, I swapped U and W here. But the point is, for all extensions of W, this code's gonna send, sorry, and then elements X and more codes A such that A is oops, that's a slight typo, but so that A is evidence for that X satisfies phi at U, then there should exist a cover, and we only require stuff to evaluate on that cover. And this is to sort of bake in the fact that, like, you know, we don't, when we're talking about sheafified stuff, we don't always have values straight away. Sometimes we need to wait for them. But so you can define this, and this will give you a tripos, and it'll be like really annoying to do anything with it because like you're gonna have a million subscripts around, and like maybe you can already tell because of some of the typos I've made. It's like really painful, and so the solution is you use your sheaf square. I was in Sheffield on the way here, and I remembered that, so I had to like run out of the train. Well, it was I was changing trains there anyways. I didn't miss my train. But so we're going to use a law of eternity topology. Like, doesn't matter so much what it is, but it's a way that's going to let us talk about covers internally to some type theory, or like to our type theory, or to, you know, higher order logic. And so yeah, it's a modality that sends propositions to propositions. And so like P should always imply box P. It needs to be idempotent and like preserve conjunction. The intuition is that if box P holds, then we don't know that means we're at a world where there exists a cover where P is always true, but P might not be true right now. Of course, like if P is already true, then you know that there exists a cover, namely like the one given by everything, because there's this sort of monotonic flavor to things. But so once we have that, then we can start defining stuff internally to a topos. So like ultimately I'm interested in pre-sheaves, but like, you know, we would sort of we don't have to work with pre-sheaves. And it sort of makes it clear what works generally. So if we act for an actual internal PCA to this topos, which in the case of pre-sheaf is going to be similar to this index application thing, then the predicates are now going to be internally, that's just this function space. And now toward the realizability predicates, it's a lot simpler. We're saying there exists this codes such that for all X and A realizing or inside of phi of X, box, so this is where I'm saying there exists this cover, and then at the cover, we know that E applied to A is going to terminate, and that's going to be evidence for psi of X. But so that now there's no explicit mention of worlds anymore. And so you can show that this gives a tripos. I found out last week, so this actually appears, this already, like this exact definition appears in Jaap van Oosten's PhD thesis, which I wasn't aware. But so later on, well, so he sort of introduces it, but ultimately he then sheafifies the PCA A because that simplifies the situation and lets you like remove the box. And for his purposes, I think he was trying to get this proof of the Young's theorem, like that's enough. But here we don't want to necessarily sheafify A because I think once you sheafify A, you're like adding a lot of extra realizers that didn't really exist before. And so you sort of lose some power over like what is and isn't realized. But so this gives a tripos. And then, yeah, the next steps from there is first basically, yeah, this is like what I've been working on and is like now currently typing up. But so now we want to talk about these like sheafy natural numbers that are sort of not pure. But so for that, we still then need an actual sheafification operation on the realizability topos associated to T. Thankfully, like I don't know that it's like yeah, don't have time to talk too much about it, but like so we can actually define that and it works fairly straightforwardly, and that's quite fun. But so that now with this, we can actually start like investigating all of these different choice sequence axioms. Choice axioms is misleading, I've realized. But yeah, the choice sequence axiom. So that's something like to be done next. And then like I still want to return to the original use case we had, which was for Markov's principle, and see like how much of that story still carries on in this setting. But yeah, that's